Are you, Gustavo? We don't hear you.
In principle, I should be ready to discuss. My microphone doesn't work. Okay.
All good.
All good. All right. Let me share my screen first. Okay. Now I can see you. I cannot see you guys. So if someone wants to connect the camera, you are certainly allowed. If you are visible. Today, the plan was to discuss a bit the experiment we did yesterday and to address the problems that you had. Did someone think at all about yesterday's experiment? Thumbs up. You have the thumbs up option. You don't need to talk for that.
Push on it, please.
No one pushing it, so no one understood. This is terrible here. Oh, Fabio understood. That's great. One understood what we did yesterday. So, oh, no, only one. That's sad. I saw your test. The test was fun to see what you guys answer in the other tab, what you wrote. Very imaginative. The marks were, as an average, good. Some people were very good. Some people were good. The only thing that seems not to be so clear is why we use Hitchcock flip paste and what is the advantage of using Hitchcock flip paste. So can someone tell me what was the advantage? Maybe who is this person? I can see the name only with the people without camera. So Nicole, Ritina, can she tell us? Is she there?
Hello.
Hello.
Okay, good. With the heat shock, we can induce the flip paste when we want, so it's not always active.
Okay. So what is the practical advantage? Why would we like to generate the clones earlier or after?
If we want to induce the specific gene in a specific developmental state.
Okay, so you would first avoid, if you generate in a later stage, you would avoid the possible effects that this overexpression has in earlier stages.
Yes.
But I also include everyone understand that? Thumbs up? You guys know how to do thumbs up? Or is that you don't agree with it?
Well, my button doesn't work.
Gustavo,
Huh?
Gustavo, if somebody answers like Nicole and she's right, then you tell her that she's right. Not just to please her, but then people know that this answer was right. If you immediately ask the next question, then it's
okay.
You have to tell them this is correct, but maybe yes and no, or whatever. Okay. But if the answers are correct, it's important that people know.
I should be more.
Yeah. No, it's important to know, is it the answer correct, or was it wrong, and you ask just in a different way now. So it has to be clear. We are in Switzerland here, not in Spain.
Okay. So the answer is, of course, absolutely correct, but there's more points to it. So there's more.
There are always more points, yeah.
There's more possible correct answer. There's always more than one correct answer. So does someone see which other advantages this versatility gives us? For example,
protein interferes with an earlier stage of development and is, for example, lethal at an earlier stage in overexpression. This prevents it because we can start it when we wanted to, or start the expression when we want to with HCHOC.
So this is again good answer, but it goes in the same direction as the first. No, so we want to avoid the possible deleterious effects that it has before in development. It's good again. But the other thing that we can control is control the size of the clones? Because this seemed not to be that clear in the answers of the quiz. So I basically want to do very, very brief demonstration how the size of the clones is affected by when we give the heat shock. So imagine that at the beginning we have a
I don't see
tissue.
anything.
What?
We don't see anything.
Don't you?
No.
Do the other people see something?
I can see.
Yeah, we do, but you have to switch between screens or the person's camera. So there are two.
So I'm the faultive guy. Okay, sorry.
That was correct answer too. I'm sorry.
I'm not done yet, but I'll get there.
Okay, so let's see. We have a tissue during development multiplies itself number over time. Normally exponentially if the growth rate remains stable. So if we generate the clones in this stage, when we have only one cell, basically we will have only one clone, but very big. All the cells will be red in the final tissue, okay? Whereas if we generate the clone in a later stage, let's say here, and only one cell gets activated, then only 1/4 of the tissue will be activated. So the clone will be smaller, okay? Depending on when we give the heat shock. If we give the heat shock rather late, only one cell division before, then our clone will be of 2 cells. You understand that point? So when we give the heat shock, we'll condition the size of our clone, okay? The cell number of our clone. All people that didn't have it that so clear yesterday in the quiz understood it now. The quiz remains open. Oh, Sarah, thank you. Thank you. She knows how to use it. Oh, another one. This is amazing. So clonal size, very easy. Today, just we finished with what we did yesterday. We are gonna go briefly through the result and we discuss the adult phenotype. Did someone think how the adult phenotype should look like? More or less. Nuno does like this. I imagine that's more or less thought. Did someone else think? Not much. You just went to sleep right after. Okay. I'm gonna briefly show you what we saw yesterday. So yesterday we visualized the DBP targets and all of you saw this kind of image. This year I don't have to go in detail because I made sure you saw this by giving you the image of what you should see. And we saw that reporter was activated in the cells that were seeing DPP, and DPP was expressed here in the middle in this stripe and dispersed towards the sides, activating that reporter, that GFP, okay? In a graded manner. You can all see the gradient, I hope. You can see the gradient of activity. And we also saw that Brinker, with this special reporter based on a GAL4 and a UAS driving the expression of an M-cherry protein, Brinker is expressed in an inverse pattern to that of that. Okay, because it's repressed by DPP pathway. Here in this image, it's not that clear to see, but there is a gradient here of activity, while one is inactive in the close to the source, the other one is active, and there is a gradient of activity. The reporters are not that sensitive, so we cannot see that well in the interface between both. Okay, this was clear for everyone. Did someone has any doubt of how the GAL4 US system works or why the pattern is like that?
No doubts, but maybe they had questions.
Oh, questions. Sorry, my English didn't improve since yesterday. This is a terrible thing.
Maybe one question about the GFP signal on the left side.
Yep.
yesterday we talked about the gradients and that we should have either GFP or M-cherry, more or less. What is the reason for this green line on the left side that we can see, but not on the on the left side? Well, whatever you mean.
This.
Yeah.
Okay, I'll explain. So if we would cut this tissue here and look the orthogonal view, now we are looking from the apical side, okay? If we would cut the tissue and look from the orthogonal view, the tissue would look like this. There's a chunk of cells, and this is all the cells are like this, are elongated, is a pseudostratified epithelium, meaning that the nuclei are distributed, not all in the same, but all cells touch apical and base. Okay? This would be how this would look like. And indeed, these cells in the middle would be that positive, and this will be M-cherry positive. Okay? This is clear for everyone. The orthogonal cut. Very easy. What I didn't tell you, because we went rather fast through it yesterday, is that the tissue is slightly more complicated. The tissue is not only comprised of this pseudostratified layer of cells, but also it has a very thin membrane of cells of very different nature. Cells that are no longer very long and very rectangular-like. These ones are kind of, it's the so-called squamous epithelium. It's called peripodial membrane, okay? And the cells are polygonal, very big in this case, and very flat. And this surrounds the whole tissue, okay? Like this. You see how the tissue is more or less? So it's a sac that in the middle has a lumen. Okay? So two epithelia that are surrounding a lumen. One of the epithelia is very thick and the other one is very thin. Okay? So these cells that we are seeing there are actually the peripodial membrane. Okay? That also some of them express that reporter. And since this image has been taken a lot, you know, you cannot distinguish well. It's not a very thin line where you say, okay, I'm now only seeing this plane, but you're seeing a lot. We are seeing this whole chunk. And of course, you kind of impose the peripodial on the disc proper. So we are seeing the peripodial at the same time as the disc proper, and the peripodial has some expression of that. That's why it looks like it's overlapping, but it's not overlapping. One is on top and the other one is below. Okay? That clear now? Good. Thumbs up. I see new faces today. Some people got camera. Some people lost camera. It's good. Any other doubt of why we don't use, why we use the GAL4 system at all?
No doubts, Gustavo.
Or questions? Is there any way to mute? No.
No.
No, there's no way. So, questions. Sorry, I will improve my English. I promise. Next year, it will be completely different. So if you cannot pass, I promise you, I will say questions.
Okay. I have my doubts.
You have your doubt. I also have doubts every morning and every night. So no more questions on how the system works or why. Now you can take this system home. You may not care about developmental biology anymore. You will do your maybe microbiology, and maybe one day you say, okay, we could implement some transcriptional circuit, very easy transcriptional circuits to express our desired gene based on our desired promoter. And you may use this concept of the GAL for UAS, maybe with other transcriptional factors. Okay. So we go to the gain of function. This we also did yesterday. Basically, this is the general scheme. Do you remember we have tubulin promoter? Okay. and then driving the expression of DPP. But we have the two FRTs here and here, and a transcriptional terminate. What Markus insisted yesterday is that there was an extra marker in the middle in order to visualize where cells, in which cells the FRT recombination has occurred. So this marker.
Sorry, but are you drawing? Because if yes, you have to switch the screen.
Oh, I don't know what happened. I'm drawing everywhere. Sorry, technical issues. Background music. Where is now the video guy? You should put some video. Ah, no, video not necessary. Okay. Now you can see. This was what I was explaining you in the background while you didn't see. Tubulin promoter, driving the expression of DPP with the two FRTs in order to make DPP expression inducible, and in the middle, a transcriptional terminate. Markus insisted, okay, but in the adult, we will need a marker. We will need a marker to know which cells, in which cells FRT recombination has occurred. And this marker, it's a marker that it's only visible in the adult. It's called forked. Forked is a gene that is required to make bristles straight. The bristles are the hair of the fly. When forked is not there, the bristles are like this. When forked is there, the bristles are straight. Okay, so we can spot which cells, which cell territory is producing DPP and has undergone FRT recombination, because the bristles, the hairs in that part of the body will be forked, will be like this. Okay, so as you can see, only when flippase force this system to recombine, forked is released. Okay. Of course, we will need this system to be in a mutant background of forked, because we want to remove forked to see the mutant background. But if we have the wild type copy in all the cells, then the cell already has a copy. So these flies where we introduce this system have to be in a forked mutant background. Everyone understands that? It's a bit complicated. Easy? Thumbs up? Thumbs up. Okay. So our crossing scheme was the following. We have a fly, a virgin. Okay. You can all see this, no? Now you can see it has changed. A virgin that has fork mutant. Okay. Important, the fork mutant, because otherwise we will not be able to see if there's a fork wild type copy. Then flip is under the influence of heat shock. Our cassette that includes the tubulin forked DPP and a balancer chromosomes, okay? I told you yesterday, we cross these with wild type flies, wild type males, in order to look at flies that do not have the balancer chromosomes, to get rid of them, okay? So we cross them with males that are all wild type in all the chromosomes, okay? Easy. And we give the heat shock, 10 minutes, 37 degrees at 40 hours, something like that. Oh, Martin's here. Now I'm really under pressure. And this is the genotype resultant. Okay? These are the possible descendants of that fly. Some of them will have the balancer chromosomes. Okay? And some of them will have our insert, our cassette. That's very clear. So half of them inherit one and half of them the other. That X chromosome, it's also, it segregates, but the X chromosome, it's in homozygosis, okay? So all the descendants will get the heat shock flippers. The males will get it in hemizygous conditions, will get the heat shock flippers over the Y chromosome, And the females will get the hitch of flip base over the plus chromosome. Okay, you see that? Hitch of flip base in females will be in heterozygosity and in males in hemizygosity. You see, this is a female over plus and in a male over Y. Someone has any idea of which ones we will take, which of these 4 genotypes we will take in order to analyze the phenotype? Martin left, so Martin knows. Someone else has any idea? Only one of these 4 genotypes is the correct one to analyze in the adult.
Only the males, and then if you get females, you can be sure there is a flip base.
So, but I said it's correct, partially correct, but you said if you get females, make sure that they have the flip base, no? But I told you flip base is homozygous in the mothers. So all the progeny get the flip base. Okay, so all of them have the flip base, but you have to take the males for a different reason. Okay, and the reason is related to this fork mutant background. I told you that we will only be able to spot the forked phenotype if we don't have any endogenous copy. So we need to have a forked mutant background, okay, rescued by our cassette, and then conditionally removed it. Okay, so if you look at the males will have 1 copy of forked here, and then the Y chromosome. The Y chromosome has no forked. It's the X chromosome that has the forked. Okay. In this case, in the case of the female, the X chromosome, one of the X chromosomes has forked, but the other one has normal. It's wild type, so it's forked plus. Meaning that in the resulting clones, we will not be able to see the clones because all the cells in the tissue will be wild type, will be forked plus, not wild type, but forked plus. Everyone understood that? Thumbs up, or better, if not, if you didn't understand, say it. Okay, I see a lot of thumbs up. Easy, you're very good at genetics. Right. Okay, so we will analyze the males in the adult, okay? So let's go at the adult tissue. Martin prepared this slide some time ago, and he was nice enough to take photos of the bristles on a wild-type wing. This is zoom in into a wild-type wing where you can see the bristles. The bristles are all straight. This is wild-type. All these cells are 4 plus. They are wild type. Okay? Get familiar on how this looks. This is how forked mutant look like. Very funny. It's like if you do the permanent to the flies. So the bristles now look curly. Okay? So now,
Gustavo,
yeah,
maybe worth mentioning that each and every cell has 1 bristle. So each and every cell, if it's forked,
yeah. So in
plus it makes a straight one, and if it's forked, minus. Every cell, every bristle reflects a single cell.
Yeah, in the wing specifically, in other parts of the cuticle of the fly is not like that, but in the wing, each cell contains one bristle. Okay, and this is very good because we can then count the bristles and know the number of cells that there are in the wing. Okay, so now let's look at how the wings look like. I told you yesterday, I briefly introduced that in the wing we have a very stereotypic pattern of veins, counting L1, that maybe Markus knows what L1 is. For me, it's always complicated. It's here. Okay, not that easy to spot like the other. And then L2, L3, L4, and L5. And then we have 2 cross veins. Okay? Shinya already showed you this pattern, I'm sure, this morning. So we said yesterday that the DPP expressing cells are in this region, in the central part, okay? And that will be expressed towards this region. And the laterals will be Brinker positive. Also yesterday, you told me that we only get duplications when we end up in one of these Brinker positive areas, okay? You told me that yesterday. So if one clone ends up in the, let me see, in the posterior domain, what would you expect? Someone can connect the audio? Maybe not Markus. Markus knows. Maybe Simona, that doesn't have camera. No, sorry, Simona. Can you hear me? It's like connecting to the outer space. I cannot see anyone. Maybe Fabio wants to talk.
Yeah, you will get additional wing, because then you have 2 gradients, and now we will get more. You will at least 2 more.
This is super good answer. So
yes, this is super good.
but
the scheme you drew
where?
is absolutely misleading. Not the scheme you drew just now, but the wing, because you cannot induce, if you induce a clone at that level of the wing, you will get nothing. You see? So what I want to mean, you cannot induce a clone in that area of the wing because the wing is already made.
Of course.
Yes, yeah. I know, of course, yeah. That's true. But if you would try to think about here, you cannot lead to this duplication. So you cannot think about the adult wing when you induce there. You have to make a drawing with the larva, with the imaginal disc.
So did you guys understood what the point that Markus wanted to make? That of course
I think they can't understand. But let's say you make a clone here where you drew it. Can you point to it?
Here. Let's say we make
let's say the other one, because you show a posterior clone afterwards. So there, let's say you make DPP there. What we say is you induce growth and you induce patterning. But of course, what do you want to duplicate? Vein 5. Vein 5 is already there, this one. So it's counterintuitive to do it there. I think you have to draw the imaginal disc and then start from the imaginal disc.
Okay.
You know what I mean, Gustavo?
Yes, I know what you mean. I'll draw the imaginal disc for the guys. Okay. So we get the zoom in, and I'll draw the imaginal discs. I told you yesterday that DPP essentially or mostly specifies vein 2 and 5. So we are going to draw the wing pouch. The wing pouch, you remember, it's the part of the wing that will give the part of the wing disc that will give rise to the wing. DPP is expressed in the central area. Okay. And it will create this gradient of activity that is very intense in the middle and go towards the edges. Okay. If we look at this in a schematic way, it would be like this. Okay. Being the source here in the middle. This will place the veins here and here. Okay. In one case will be vein 2 here, and in the other one will be vein 5. Okay. That clear? Now, the clones that we are inducing in an early stage, of course, when the tissue is still susceptible to change a lot. Okay, so just imagine that we are creating, this is an earlier stage, we are creating these clones in this stage, and we have the endogenous source, and we create this alternative source. Now, this small disk will give rise to something completely different to this. Now we have this type of disk. We have here that very high, the endogenous one, placing the banes 5 and 2, okay? And we have a new source of that, okay? That will try to place, it will create its own gradient and will create growth and will pattern too. So at certain distance, at certain level of DPP activity, it will try to create another bane, okay? And this bane, depending on which compartment you are, will have different fate. We'll be able to have a fate of bane 5 if we are in the posterior compartment, okay? Or a fate of bane 2 if we are in anterior compartment. Okay, depending when.
Gustavo,
yes,
it will generate another vein too, more anteriorly.
It will generate, depending on where the clone is specifically.
It will generate another vein too there.
So yep. It will generate another vein too, because you generate growth all over your surrounding, okay, and you create the gradient. So you are creating another developmental scenario where you have now another big chunk of cells and you have a new gradient, so you will place another vein 2. If you are in anterior, you put veins 2. If you're in the posterior, you will put vein 5, okay? And the distance of these veins will depend on the amount of DPP signaling that you have. So let's go, it's good like this, Markus.
Yeah, draw the double gradient below this disk, then it will be clear why it's vein 2 and where it is.
So we have this, and now we have a new source. Like the developmental field in this wing is like this, okay? So we have clear only one source and only 1 or 2 gradients to each side. But in this case, we have increased now the wing is wider, okay? And there's a new source, okay? I'll draw the source too. This is the source, and this is the ectopic source, okay? If it's vein 2 or vein 5, I told you it's depending on which compartment we are. So if we are in posterior compartment, we will make, here we'll place vein 5. But since all this outgrowth is in anterior compartment, we will place vein 2, and vein 2. We will place new veins.
Each time at this intermediate DPP concentration, vein 2,
yes.
vein 2, vein 2.
Cells are thought to respond to a specific concentration of, in the classical model, a specific concentration of DPP or DPP signaling. So it will be more or less at similar ranges. So now the adults that we have to go to the tutorials. I'm sorry. So this is the phenotypic consequence of a clone that has end up in the posterior compartment. What we can see here is the actual normal source of DPP. And the new one, it's probably in the posterior, but we don't know where the source is unless we look at these small bristles that I told you. Only where the forked bristles are, there will be DPP, ectopic DPP producing cells. So if we would be able to, this is not good enough resolution, I'm afraid, to spot them. I'm sorry, I think I cropped the forked ones, but it will be something here. Sorry, when I transfer this to PDF, some things were gone. Okay, here is where the forked cells are. So here we have vein 2, vein 3, vein 4, vein 5. And here we have an ectopic vein 2, an ectopic vein 2.
Who? Vein 5 is vein 2, vein 3 is vein 4, vein 4 is vein 4.
Oh, yeah. Sorry. The other way around. I make this often.
This is a posterior clone.
Posterior clone. Okay. So this has fate of vein 5, of vein 5, and vein 5. Everyone understands that?
Why is it now counted the other way around?
Sorry?
Yeah, first you counted it like from the bottom to the top, and that was obviously wrong. But why? Why is it now the other way around? Or was it all when you see the slide before?
Can you go to a wild type wing, Gustavo?
This is a wild. Wait, we must have a wild type wing. Here, maybe.
No, it's clear. It's all clear. Got it.
It's clear?
Yeah.
Does someone have this doubt too?
I mean, it's very easy to see L1, L2, L3 up there. The margin, the edge of the wing has very large bristles. So you know. Can you show them these very large bristles?
Okay, so maybe Markus is trying to translate the question because you didn't finish the question somehow entirely, but it's possible to distinguish if we are in the anterior or the posterior compartment, because you see these bristles here in the border, the wing margin. They are much thicker, very different to these ones. So by looking at the border, we can know whether we are in the posterior or the anterior compartment. Okay? Good. Now, what would happen if the clone ends up in the anterior compartment? Not in the posterior. This is what happens. Okay? And this conceptually is very beautiful because it demonstrates that DPP is sufficient in order to generate growth, but to induce also pattern. Okay? Because the loss of function doesn't tell us anything, like Shinya was probably telling you before. The loss of function is just a tiny wing. What can you say? Maybe DPP is necessary to specify the wing, and if you don't have it, you don't have anything. So, but this kind of experiment allow us to say, okay, DPP is sufficient to generate a wing by itself, but the wing that we are generating, it's very special. It only has vein 2s or vein 5s, and it can only be generated in certain territory. So this is the way in developmental biology that you use to approach a complicated problem. Okay? We very often recur, especially in the past, to gain-of-function studies in order to see what a gene can do. This happened also, for example, with the Hox genes. Very paradigmatic example. We didn't know what the Hox gene did, but Markus can tell you for sure, when all of a sudden you get the Hox gene where it shouldn't be, the structure changes its fate completely. Instead of having antenna, you have legs. So somehow this gene must be related to specifying the tissue, to deciding, selecting what those cells are gonna be, okay? So now I want someone to tell me where fork cells should be in this new wing. In the duplication. Oh, Basil, hello. So someone, for example, oh, I cannot tell the names of the people that have camera. Any of you guys, I don't care. As Markus told me yesterday, we have the whole day. You can be here, we can be here, wait.
Between the two veins of the additional wing.
Okay, so you would expect it to be, sorry, technical problem again. I cannot promise it will not happen again. now. Okay, so you claim it will be there. Okay, and then what kind of vein will be this one, and what kind of vein will be this one?
2. So both would be vein 2.
Both will be vein 2. Okay. We also, this is good. It's perfectly correct answer. We also said that vein 1 is this, the one in the margin. So here would be vein 1, and here would be vein 1. Okay.
Actually, can you go? I'm sorry, Gustavo. Can you go back to a wild type wing?
No, but can I ask them why we know it's vein 2 and not vein 5? And then we go.
Yep.
So do you know why this is vein 1 and 2 and not vein 5? How can we distinguish it?
Because they're in the anterior compartment.
Sorry?
Because they're in the anterior compartment.
Yeah, but you could have an outgrowth of the posterior compartment in the anterior compartment. But there's a signature in these wings that tell us, okay, these are anterior wings. Which is the signature?
It's the bristles on the edge, which are way larger than the posterior compartment.
That's good. All these bristles are characteristic, as we can see here in the wild type one, of the anterior compartment. You don't see them in the posterior compartment. You see only in the anterior, and that's how we can tell this is all anterior. This is a mirror, it's a small mirror wing of the anterior compartment that comprise vein 2 and 1, properly patterned, but they are small, probably because this source of DPP was not that big to generate a huge outgrowth. Okay. And here is the answer. Martin has spotted all fork cells, and we can see all the fork cells that in red. So as he said, so those cells have to be in between. We have some here, but these ones seem only to account for this small vein. Okay, Markus, sorry, which was your?
Yes, do you have a wild type wing?
I should have a wild type wing, but maybe it was superposed in the PowerPoint and it went out when I generated the PDF.
Because vein 1, of course, the way you drew vein 1 now, it includes, so here, this is good.
This is
vein 1, stop.
This is still here.
Vein 1 stops, exactly. Vein 1 that's so, vein 1. From here, from the beginning, yes, that's vein 1. And then it's margin, the rest is margin. And vein 2 goes then down to the margin. They all go to the margin. But once the margin stops, it's not vein anymore. So vein 1 is very short. So yeah. And you can see it actually here, the vein 1. You see this V-like structure.
Okay, so this is just a image where we kind of amplify the margin so you can see these bristles are of anterior origin. We will not go into detail. This is why it's vein 5. And this, I just wanted to include it. Martin had it in his original presentation, and I think it's very good. You remember what DPP stands for? Oof, no way, too complicated. It's something like decathlon. So DPP stands for decapentaplegic, okay? If you like tetraplegic or someone that has a major problem in different parts, okay? So decapenta, you know that decapenta means 15. So it presents 15 different phenotypes in different parts of the body. So DPP, as you also see in the reporter assay where we saw where DPP signaling activity is on, is also active in numerous places, okay? And it has a function in many of these places. This is an example of what happened in the gain of function clones in the legs. You start getting dual legs. This would be a wild type leg if it weren't for this Small outgrowth. This is a wild type black. Now, wait. You cannot see it again. It stopped. I'm very sorry. We'll finish. This is last slide, I swear. Share. Okay. This is how a wild type black should look like if we obviate this kind of small thing. Okay? And when we start having ectopic DPP activity, we can generate new legs. For example, this is a mirror image duplication here. So you can see that DPP has also patterning and growth responsibilities in other tissues, okay? And this happens in many other places where DPP is important for patterning and growth. In the antenna, it happens in the legs, in the wings, in many places, okay? Someone has any question? Question, Markus. That I nailed, huh? Any question about it? Thumbs up. Thumbs up.
Yeah.
Oh, question.
About the slide with the veins, with an additional vein 1 and 2.
Yeah, that's a good slide.
Why do we? Well, somehow it's obvious, and maybe I ask it with the additional wing. Why do we have this shape or this hair structure all around the whole wing? The additional. Why do we not have like the other wings this change?
So the change that from here down you have normal bristles and here up.
Yeah, somehow it's obvious because you only have 1 and 2.
Yeah, so I'll tell you. So all around anterior compartment, so this is all around here, the margin has these special bristles, okay? This is specific from anterior compartment all the time, okay? And posterior compartment don't have at all. Now, we said that DPP can provoke growth and patterning depending on which, on where the clone starts, okay? But it cannot change the fate of the compartment. If you're in anterior compartment, you will only be able to generate patterns of the anterior compartment, meaning vein, if you're in the anterior, vein 1 and 2. But also all the tissue that gets outgrowth will have a margin of anterior compartment because you are an outgrowth of anterior, okay? So as the wild type part of this tissue, you have anterior in the, you have these bristles in anterior and you will have it in all your duplication, okay? You don't have the transition because all the cells there are anterior and therefore the margin is anterior, okay?
So then I have another question.
Can I give an answer too?
Can I have an additional question? Maybe you can answer that too.
Yeah. Yeah.
If you somehow can implement veins 5 anterior, will it then become also no, the other way around, sorry. So if you're able to have a vein 5 which is posterior and then you have a clone anterior, will it then also change? You know what I mean?
Yes, I know what you mean. Can I answer quickly? I answer the first question, and then you should be able to answer your own question. So I could ask you, what is the difference between posterior cells and anterior cells? And we might have forgotten, and it's all posterior cells, each and every cell in the posterior transcribes the transcription factor engrailed. All of them. None of the anterior cells have engrailed. So if Gustavo would show where engrailed positive and engrailed negative cells would be on that slide, whatever is below the red line, every cell makes engrailed. And whatever is above, and engrailed is a transcription factor. So if you would put into one of these margin cells in the upper lane, you would put engrailed, it would make a small bristle. It's all about these transcription factors expression. Engrailed makes posterior, no engrailed is anterior. So it's the lack of engrailed that makes these bristles so large in the anterior, and the presence of engrailed that makes it so fine. So if you play around with engrailed, you can change bristle sizes, but you have to be careful. Engrailed induces hedgehog, and then you make DBP around, so a cascade starts. But it's the presence or absence of this transcription factor that makes each and every cell to look either in an anterior way or in a posterior way. So every vein 5 cells, you can only make vein 5 cells if you have engrailed. If you try to make veins in an engrailed minus territory, it will never be 5. It can be 1, 2, or 3, but it can never be 4 or 5, because that requires engrailed. Whatever is posterior requires engrailed. All the differences require this one transcription factor. So if you want to make vein 5 in the anterior, you have to provide engrailed to these vein cells. If you would express engrailed sort of in these vein 2, it would be vein 5. Problem is you generate hedgehog disperses, induces DBP, and then DBP induces yet another growth. But you see, you have a master control gene which controls the fate of each and every cell individually. A bristle from an engrailed plus cell in the margin will be fine, and the bristle in the margin of an engrailed minus cell will be very large. And this transcription factor controls the whole morphogenesis of these bristles.
Much more to the point. Thank you. So you got it, no? You don't need the answer anymore. Yeah, me neither. Good. So anyone has any doubt that could be translated into a question?
You can also have questions instead of doubts. Gustavo.
So, or you can, if you happen to have questions, you can send me an email. My email is in Markus' website, okay? Or you can ask Martin, or you can ask Markus, or you can ask Henry, or any of the other people. We all should know this. Okay? It's good? It's good? Nice.
It's all good. So you can
go to your...
You can make a break and then go into your tutorial for the paper discussion.
Yeah, maybe
in 10, 15 minutes or so. And then you can stay in there until any time you want.
Or not. I mean, reasonable. Be reasonable.
3 people. Have a nice afternoon.